Hello, everyone. We are the Astrocultivators representing the California State University of Northridge team, and today we will be presenting our entry for Phase 2 of NASA's Deep Space Food Challenge. Our team consists of Elliot Sadler, Anthony Morales, Neville Elia, myself, Jasmine Glover, and our team of nutrition experts and administrators from the CSUN Magaram Center for Food Science, Nutrition, and Dietetics. Let's now begin with a system overview. We'll take a look at each individual system of the enclosure. Here is our overall enclosure and self-monitoring environment. First, we have the electrical system, which contains the control unit and the electronic components of the enclosure. Next, we have the RGB plant lights and harvest collection bin. Following this is the enclosure support system, which provides stability as the robot arm is in motion and prevents torque. Here are the NEMA 32 motors that have a 40:1 gear ratio and are positioned on tension belts, which allow for the raising and lowering of the gantry system. Following this is our gantry and robotic arm in one step. The gantry is responsible for the placement of both grow lights and arm, in addition to allowing for the grow lights to be placed at optimal distances from the plants that can be adjusted at different growth cycles accommodating for plant height. Then we have a universal robots cobot, specifically the UR3E model, which is safe to use, simple to program, can operate within distance of people, and features a suction end effector for picking and placing of the harvest. This feature is self-contained and does not require the use of an additional pneumatic system. Now we will take a closer look at the carriage system. Here we've provided a closer look at the carriage's internal components and assembly in an exploded view. The top and bottom are completely separate components that are only connected by a thrust bearing that supports the weight of the plants and carriage components. All of the components are designed with the intention of utilizing 3D printing technology, the flexibility of an adjustable system, and in addition allows for the upper half of the carriage to spin a total of 360 degrees. The drive system uses a friction-based belt system to power 14 carriages that travel around an oval rail. The thrust bearing, the wave gear, and the mounting plate are visible beneath the carriage assembly. Each individual car's engagement to the friction belt may be adjusted, and the counterforce pieces visible here can slide in and out to adjust the cart's alignment as they tend to go in and out of path during travel. As the train is pushed through the drive system, the wave gear above engages with the outer wave gear and rotates each plant 360 degrees through the scanning area. Using hyperspectral imaging in 900 to 1100 nanometer wavelength ranges, each plant moves through the scanning area in which the cobot will then scan every plant to monitor current health. Now is presented the arm in action. In this clip can be seen the arm using the suction end effector to pick the tomato and next place into a container. In this clip, here we can showcase the ability of the cobot to maneuver to different positions needed for harvesting or monitoring. Next, we will have Neville Elia to discuss the overview of the AI system.
Hello, my name is Neville Elia, and today I'll be demonstrating the object detection process. So to begin your labeling, you would first select the image that you wish to train your model with. So we're going to be using this one. Press W and you select the area in which you want to make a label for. And for this one, we're going to name it tomato. And you'll do this across the whole picture until you get something like this. So as you can see here, now we have all the tomatoes labeled. So now we can choose if we want to move forward to the next picture, or maybe we want to label all the leaves, anything our model needs. Now to show you guys what type of results we can expect from our model. So here we have a few photos that we ran our object detection on. As you can tell, our object detection was able to identify this tomato plant and name it as a sprout, as it doesn't have its significant tomato features yet. And it will continue to label it as a sprout until significant tomato-like features are shown. So as the tomato plant grows, it eventually will identify when it has the features of a tomato leaf, and it will begin to label the leaves as tomato leaves. As you could see, it's clearly labeling which tomato leaves are clear and identifiable, and will continue to label the ones that can provide us more information. Last but not least, here's a video of live detection on our tomato plant, where it identifies all the tomatoes.